Good morning, afternoon, and evening to everyone joining from around the world. My name is Joshua Subel, and at the time of recording, I am a final year PhD candidate in engineering at the University of Cambridge. My research focuses on the fuel efficiency of trucks, and today I will be speaking to you about the impact of coasting on fuel consumption of heavy goods vehicles. Globally, there has been a colossal effort to improve the fuel efficiency of various modes of transport, with cars and trucks often taking the spotlight. However, despite the wealth of resources that have been dedicated to this endeavour, the UK is yet to see nationwide results. This figure shows how the fuel efficiency of UK HGVs, measured in miles travelled per gallon of fuel consumed, has changed since 1990. And we can use this data to develop an insight into whether legislation and innovation have actually wrought positive outcomes. And among the most influential pieces of green legislation are the Euro vehicle emission standards, which have been updated and revised fairly regularly since they were first introduced. And there has been some progress, especially regarding light goods vehicles, which can travel about 25% further on a gallon of fuel than they could in 1990. Slightly heavier vehicles have seen a more modest improvement, but when we consider larger vehicles still, a different picture begins to unfold. The bottom four lines relate to articulated HGVs and the heaviest groups of rigid trucks. But despite the introduction of 3 new Euro emission standards and massive efforts by academia, industry, and policymakers, these vehicles are no more efficient today than they were in 2005. And this has severely hindered efforts to decarbonize the transport sector. In 1990, road freight contributed approximately 25% of domestic transport emissions. But today, this proportion is more than 30%, with light goods vehicles and vans counteracting all the progress made in buses, shipping, and other modes of transport. Consequently, the UK's total transport emissions, the largest polluting sector in the UK, have remained mostly level. So in the current climate crisis, road freight is a critical issue, one which we have not yet tackled effectively. So what exactly is eco-driving and how can it help us cut emissions? Broadly, eco-driving has been described as all operational decisions which improve fuel efficiency, but this definition is quite limited on its own, so it has been expanded in the literature to encompass 3 aspects. Strategic, i.e. choosing green vehicles and following good maintenance practices. Tactical, such as planning efficient routes and maximizing payload. And operational, which concerns how the vehicle is actually driven. There are far too many aspects of operational decisions to cover them all here, but some critical aspects of eco-driving are smooth acceleration and braking, de-speeding to reduce aerodynamic losses, and the key topic of today's presentation, coasting, which we will discuss in greater detail in the following slide. But first, why bother with eco-driving? Well, most studies have shown that eco-driving practices can improve an HGV's fuel economy by 5 to 20%, depending on the driver and the service requirements of the truck. And these benefits can be realized with minimum investment in new technologies, and many of the practices which emerged as early as the 1990s are equally effective today. But if it's so cheap and easy, why hasn't eco-driving had a notable impact on transport emissions? The most convincing explanation that I have found in my research is that eco-driving is still too ill-defined. There is little agreement in the literature on what constitutes eco-driving and which driving styles lead to greatest fuel efficiency. Some authors have noted the need for individual eco-driving practices to be methodically tested to build a consensus on eco-driving which can be widely adopted. This work investigates the impact of coasting and highlights the significant potential for fuel savings through simple and intuitive strategies. Now, what exactly is coasting and how does it help save fuel? In the simplest terms, coasting refers to when the driver releases the throttle and allows the vehicle to roll under its own momentum. Owing to the large masses of HGVs, trucks can roll for 1 to 2 kilometers without losing enough speed to disrupt the surrounding traffic. This distance can be extended even further if downhill stretches are exploited to recharge the vehicle's kinetic energy. So consider a vehicle traveling up a slope by applying a tractive or driving force at the wheels. This motion is resisted by aerodynamic drag, uphill gradient forces, rolling resistance, and inertial forces, which are equal to the product of mass and acceleration. Applying Newton's second law, we get this expression, which simply states that the driving force is equal to the sum of resistive forces. This is also a good time to introduce the mass fuel index, which is defined as the ratio of fuel to the product of the vehicle mass and distance traveled, i.e. how much fuel was used to move 1 ton 1 kilometer. Let us consider a practical example using in-service telematics data from a 30-ton articulated vehicle. The vehicle first accelerates to 90 kilometers per hour, and clearly the driving force is positive and fuel is burned rapidly. The throttle is then released and the vehicle starts coasting. The driving force is now 0 and the vehicle can coast for more than 1 kilometer without burning any fuel. At around 55 kilometers per hour, the vehicle starts braking to enter a roundabout, still not using any fuel until the driver exits the roundabout and reaccelerates. In light of these resistive forces, how important is coasting? The figures appearing on the screen are generated from in-service telematics data for the same 30-ton vehicle discussed previously. We see the speed profile on the top left, where the vehicle coasts, brakes, reaccelerates, and repeats. In the top right, we see the fuel flow rate, and while the vehicle is coasting, the fuel flow drops to 0, but spikes again during reacceleration. We must also consider the road gradient, shown in the bottom left, and while most of the stretch of road is flat, there is a fairly steep hill where the uphill and downhill gradients are clearly visible. The rate at which the vehicle does work to overcome aerodynamic drag, we call the power component of drag, now appearing on screen. Under these conditions, the power components of drag and rolling resistance are quite similar. But despite the road initially being flat, the power component of the gradient forces has a similar magnitude to drag and rolling resistance. When the hill is traversed, the magnitude of gradient forces increases sharply, illustrating just how important it is to utilize gradients properly. When the gradient power is negative, less fuel is required to cruise at a constant speed or to reaccelerate. Quite often, however, the driver will need to dissipate this energy by braking if they are already traveling at the maximum speed permitted by surrounding traffics or legal limits. The power component arising from inertia dwarfs the others. Note the large negative portions where the vehicle is coasting and then it spikes in the negative direction where it is braking. While the vehicle is coasting, the vehicle is taking advantage of its own inertia, gradually dissipating kinetic energy to propel itself and overcome resistive forces. A large portion of the vehicle's energy is still wasted when the vehicle brakes, and we hypothesize that drivers can save fuel by maximizing the coasting portion at the expense of the braking portion. But coasting distance also depends on speed. The faster the vehicle is traveling, the further it can coast before it has to brake. So, is it beneficial to increase your speed in order to maximize your coasting? This is by no means a straightforward question. Yes, work will only be done on some gradients, but this is no guarantee of saving fuel. Less energy is wasted on braking, and this is a clear advantage, but a higher speed also means that more work is done both to accelerate the vehicle and overcome drag. So, will maximizing coasting lead to fuel savings? We tried to answer this question through a case study conducted on a popular delivery route in the UK. This route, displayed on the map, spans 182 kilometers from the headquarters of a large third-party logistics company, Turners Soham Limited, to a Tesco distribution centre. The red numbered markers on the map show where the route has been divided into segments of various length, allowing us to isolate and examine many different driving scenarios from the single route. Where the blue line is clearly visible, such as here and here, there are long stretches of unobstructed driving where coasting is used to overcome gradients. The red circles also represent opportunities to coast to a lower speed before braking, such as when entering a roundabout or adapting to a new speed limit. Notice the clusters are marking here and here and here, where numerous coasting opportunities arise in rapid succession. Now, the driver chosen for this study has comparatively good coasting performance, typically coasting for a total of 47 kilometers or roughly 26% of this route. However, when accompanied on trips and advised on predetermined coasting locations, coasting distance increased by almost 50% without any noticeable impact on trip duration. Now, this resulted in savings of over £3 per trip, or more generally, a 2% decrease in fuel consumption for every 10% increase in coasting distance. So let us examine how we arrived at these figures by first considering the trip as a whole. The top axis shows the cumulative coasting distance achieved by the driver, and the bottom axes show the cumulative fuel consumption. On this trip, the driver was asked to coast as little as possible in order to illustrate the extreme case where drivers are totally unaware of coasting. Now compare this to a trip where the driver was accompanied and advised on predetermined coasting opportunities. Notice the massive difference in coasting distance. On trip 8, represented by the red line, the total coasting distance is more than 4 times greater than on trip 3, the green line. But initially, this doesn't have much impact on fuel consumption at all. And this is owing to the flat roads and constant speeds on long stretches of motorway. So clearly, coasting is not a catch-all solution, and care must be taken to utilize it under the correct conditions. What are these conditions? Well, at some points between 75 and 100 kilometers, the driver encounters the clusters of roundabouts that I highlighted earlier. Coasting distance increases rapidly, and fuel savings then begin to add up. Let us now compare each of the 8 trips conducted in the trial. On the x-axis, we have the total coasting distance, and on the y-axis, the mass fuel index. And we want to use as little fuel as possible to transport the payload, so a lower mass fuel index corresponds to better fuel efficiency. These 2 tests in the top left represent the unaware driver, where our test driver was asked to avoid coasting where possible. The driver was asked to coast as they normally would on these trips to establish a baseline, and it is this normal coasting performance against which we will draw comparisons. On the remaining trips, the driver was assisted in achieving the remarkable coasting figures you see here. Now, clearly fuel consumption tends to decrease with increasing coasting distance. And while a simple linear fit may not describe the trend fully, it does allow us to draw some preliminary conclusions. Firstly, a driver who pays no attention to coasting will use 7% more fuel on this route than one who is conscious of and well practiced in coasting. With assistance, even experienced drivers can improve their fuel efficiency on this route by over 4%. But here's the kicker: without the operator having to invest in complex and expensive equipment. I also want to point out that all of these tests took place over the course of a single month, showing how rapidly the benefits of coasting can be realized in practice. Looking at individual segments of road can help us understand when coasting does and does not save fuel. Do you remember the coasting profile which we discussed earlier? Well, we can compare it to a different trip passing along the same segment of road. The purple lines that you see are generated from a trip where the driver was coasting normally but without any assistance. Notice how the driver continues to accelerate to 90 kilometers per hour, burning all of this fuel in the process. What could the driver have done differently? Well, if they began to coast at this point, the vehicle would have followed the same speed profile as on trip 7. However, they would have avoided using all this additional fuel. So the trick isn't necessarily to completely maximize coasting distance. Rather, a driver should aim to maximize coasting whilst minimizing acceleration. Nevertheless, if we look at how fuel efficiency varies with coasting distance for the individual segments that make up the route, we find that fuel consumption decreases with increasing coasting distance across a range of different driving scenarios. On most segments, coasting distance could be increased significantly above a driver's normal baseline through driver assistance, and by up to 100% on certain road segments. This led to fuel savings of up to 20% on some segments. So, if a driver consistently maximizes their coasting distance, the evidence suggests that the net result will be appreciable savings. But this total will depend on the characteristics of the route in question. So, where does coasting stand in the context of eco-driving? Based on this study conducted on a popular delivery route in the UK, aiding an experienced driver to consistently maximize their coasting distance saved more than 4% of fuel, or 3 pounds per trip. This was achieved by increasing the total coasting distance by up to 40% and up to 100% on individual road segments. From this, we can identify some practical coasting strategies, though further testing is needed to see if the same benefits are realized on various routes. Higher coasting distance resulted in lower fuel consumption, both in total and on individual segments, so it follows that drivers should be trained to maximize their coasting distance. However, on shorter stretches of road where the driver is not necessarily traveling at a steady speed before coasting, it is important that the driver coast early enough to preempt any unnecessary acceleration, since fuel cannot be recovered through coasting once it has already been burned. But these strategies are not without their challenges. Future work will focus on improving our estimates of the vehicle's drag and rolling resistance parameters and more accurately modeling the vehicle's coasting speed profile. We must also be able to anticipate when a coasting opportunity is approaching from a vast distance. And finally, we need to accurately model the speed of the surrounding traffic to predict and parameterize coasting opportunities and their constraints. And with that, I would like to conclude my presentation. My co-authors and I wish to thank Turners SOAM Limited for their contribution to the study, especially Stephen Thorpe, Sandra Bennis, and Terry Skelton, without whom this work would not have been possible. Thank you all so much for your time and attention.